engage with your fellow attendees. The connections you make here may lead to future collaborations and groundbreaking discoveries. Let us embark on this exciting journey of knowledge sharing and innovation together. Thank you for being here again with us, and let us have another great day of learning and collaboration. Thank you.
Thank you, Dr. Badr, for those opening remarks. Now we are honored to welcome our first keynote speaker of this morning. Professor H.T. Kung is the William H. Gate Professor of Computer Science and Electrical Engineering at Harvard University, renowned for his pioneering work in artificial intelligence applications, high-performance computing, and computer architectures. He also serves as the president of the Taiwan AI Academy, contributing significantly to AI education and industry. Please join me in welcoming Professor Kung to the stage.
Everybody, good morning. I'm very pleased to have this opportunity to visit the Middle East for the first time. I've had a very good one day so far. I'm very pleased to be able to communicate with you and talk about all sorts of things. So today I'm going to share with you some of the research work and ongoing work in this field. About computing. Let's see, how do I turn the page? Which button? The green. Of course. Henry yesterday showed my face. That was a long time ago, though. Okay, this is about me. Carnegie many years, Harvard many years, and my Chinese name is Kong Qiangcong. I'm 76th generation of Confucius. 2,500 years ago. My English name is Qiangcong Kong, but nobody can pronounce Qiangcong, so people call me HT. HT also stands for high tech. Okay, so now you know who I am. I will talk about one of the three very important components in AI. The first one is data, the second one is model, the third one is computing. And distributed computing is a major approach in computing, trying to scale AI computation. So I will discuss distributed computing, both practice and also ongoing research. So we all know this picture as a deep neural net model that has many neurons. You have connections between neurons. Each connection is associated with some model parameter. The training of the neural net is about minimization. You minimize the loss, namely the difference between predicted output versus ground truth output. You want to minimize the difference. So the minimization is the problem we deal with that. A standard method of doing the minimization is a method called a stochastic gradient descent. You minimize along every dimension. In this picture, we have two-dimensional minimization. In practice, we have millions or tens of millions or hundreds of millions or even more dimensions. On each dimension, we minimize. Okay, so this is the problem we deal with in training and network. It's called stochastic gradient descent. Everything is based on probabilities. Sometimes it goes there, sometimes it goes the other directions with different possibilities. So the models of AI at a very high level look like this. It's a red model that's usually is pre-trained with a lot of data. Afterwards, we fine-tune the pre-trained model for specialization or for human preference alignment. After you have these models, we do inference. We put in a prompt, then we get a response back. So that's the big picture. So distributed computing is about how to use many computing nodes, which could be some CPU cores or GPUs and so on. They all work independently over a network. Could be on-chip or could be on a data center network. So in general, it's about using distributed computing for multiple reasons. One of the reasons is to do scaling. You can scale the computation to a very large degree by using many nodes. You can also scale down a model into a small model that can, as small as a model that can fit in a human's glass. Because distributed computing gives you the efficiency, lower the energy, lower the latency, and so on. So distributed computing would be useful not only for big computation platform, but also for tiny computation platform, all based on the principle of doing things in a distributed way, so the cost can be spread efficiently among workers. The other reasons we do distributed computing is for locality and privacy. Distributed computing, by definition, you do computation in place where the data or application resides. So this is good because the privacy automatically assured. And also the communication costs can be lowered. The third reason is for low latency. Distributed computing, you do computing at the place where your data enters or data being used. So this is, you don't need to waste the time in moving the data. So these are the reasons you do distributed computing in all scales. Okay, then how do you do distributed computing? What you do is you split the computation into different chunks. You maybe split the data into 4 chunks. So the same model applies to multiple data chunks in parallel. Another way of splitting, for example, is to split the model. You break the model into 4 groups, for example. You run these 4 groups independently. Okay, so in between you have many different schemes. I will present 8 different methods of doing the splitting. Okay, I'll leave the slides to you. Okay, you can study each one. I will use probably just 1 or 2 slides for each method. These are the methods. Some of those methods are based on data splitting. Some of the methods are based on model splitting. Some of the methods are based on ensemble splitting. Some of the methods are based on spawning. You have a big model, you spawn many small models. So I go each of them one by one now. Data splitting, we're going to talk about 2 methods. One is about the stochastic gradient descent I mentioned earlier, but now we want to do it in a distributed way. This is probably the classical method of doing distributed computing for AI, is trying to do this training in a distributed way. This is a very standard kind of approach. The second one is more advanced approach. You're trying to do distributed computing so that you do a lot of local computing at the client side. You update the local models to a global model, and the global model take in all the local models input and take an average. And then the global model get updated, then the global model sent to all the clients again, to iteratively. This is called federated learning. I will talk about these two methods now. The first method is distributed stochastic gradient descent. This method is being used every day. It's the classical method of using distributed computing for AI. The backpropagation used in training works as follows. For each mini batch, for every sample in the mini batch, we compute the loss for this sample. Then for a mini batch, you take the average of the loss from all the samples. Then you compute an aggregate gradient to be used to update the weights for that mini batch. So that's the traditional way of doing things. Now, because I have all these mini batches which are independent, you can break the data into many independent mini batches. So I can run mini batches in parallel on the same model, for the same model. As a result, we have the right-hand side picture. We have data splitting, we have the mini batch B1B and so on. Those mini batches all run in parallel. Okay, they do their own stochastic gradient descent. Then the results is the gradients they computed. Then the gradients among all the mini batches get averaged. Then this averaged gradient is used to update the global model, the weights in the global model. Okay, that's the traditional way of using distributed computing for AI. Next thing is more and more important over the years because you really don't want to shift the data around. So what you have is you have the local data, all the clients have the local data in place, in their original places. You don't move them around. You do the local training for every client. So some of the client could be in Muscat, some of the client could be Saudi Arabia. They're all running on their own data, then they're trying to collaborate. They collaborate through their updated local models. The updated local models sent to a central server. The central server take the average, then get an updated global model sent to the local clients, then local clients will continue doing the local training using the local data. Now that's the basic ideas. Once you do that, the scale can be very large. You can have millions of clients, probably hundreds or thousands of hospitals can collaborate. Then the good thing is that the client's data never need to leave the client side. You do the local training locally. You only update the global model using the model without sending the cloud, without sending the data to the central server. So the data can be kept in privacy. So this is the second method, federated learning. The third method, and fourth method, and fifth method is about the model splitting. Now you are talking about the splitting a model. For example, on the right-hand side, we have a typical looking kind of deep learning network. I can insert a whole bunch of exit points. Sometimes the exit point is very close to the input, like exit 1. Sometimes the exit point is very high up. That's the traditional exit point. You can insert many other exit points in the middle. Depending on the input, if the input is easy, then you can exit earlier. If the input's hard, you exit later. Okay, so you dynamically put those access points there, then you look the entropy of the at exit point. If the entropy is low enough, then you know you have enough confidence, then we can exit earlier. So there's branches. This neural net has multiple branches where you can exit earlier, depends on the difficulties of the input. If the input, for example, is 0, it's very easy to recognize the letter 0, handwriting letter 0. But if you want to recognize the handwriting number 7, it could be difficult because the handwriting 7 can be very similar to handwriting 2. You get very confused. In that case, you probably have to go higher up, go to a higher branch exit in order to get more confidence about the classification. So this is called a branch net. One of the things I did with my graduate students many years ago. Now it's been a lot of people using it now. Another way is to statically break deep neural nets into multiple parts. Some of the parts will be running on the cloud, some of the parts will be running on the edge, some of the parts of the neural net will be running on the device. You can do that as well, so that you can get the computation done over the different places. Okay. This kind of idea also works for wearable computing, like AR, VR devices. AR, VR device, of course, the latency is the most important. Usually you cannot do anything more than 100 milliseconds in latency. You have to run really fast, otherwise the human get very confused or get sick. So in this case, you have to do a lot of computing locally on the device or on the edge. How do you split the computation so that some of the part will be done on the edge, some of the part will be on the cloud? So methods like that need to be worked out. Indeed, we use some optimization method and trying to find the optimal splitting point. Give you some examples, the kind of things we're working on now. Suppose you have a glass. That glass, on the corner of the glass, there has two cameras. One camera is looking outside, the other camera is looking inside. The latter camera looking inside is looking your eyes, looking the user's eye to decide where the gate is pointing. Then you know where user is looking at. So you're looking, using the camera looking inside the eye, you know the user is looking at this plane. Okay, so the problems of such a product, the problem is that there are two kind of things you have to do in real time. One is to estimate your gates. The second one is once you know the estimation hopefully is accurate, so you can know what the user is looking at, then you want to do object detection. You want to recognize the object you're looking at. Once you know the object you're looking at, of course, you can do a lot of inference on that object. The challenge for that, obviously, is on the glass, the model needs to be very small. Typically, we use a pre-trained model, then doing the fine-tuning, distillation, make it very small. The model we're using now today is like 280,000 parameters only, or you can fit on a small device. And you also need to do personalization. Every eye is different. Users, you need to train the model, personalize the model so that this model will be accurate for this particular user's eye. We can just use 5 impersonal images to do the personalization. Even the image, just ask user to look at one direction will be enough. All this is to make the data capturing for training easy. So these are some of the fun examples. For example, the The green dots is the predicted dots. The red dots is the ground truth one. So usually, if you do a reasonable job, the green dots, red dots will be very close. Assuming we can trust the green dots, the predicted gates, then depend on where I'm looking at. If I look at on the wall, then the problem we can use stable diffusion to generate a picture on the wall. Okay. If you don't like this particular bed, you can make it into a wooden bed. Change the bed to a different shape, different kind of bed. You're looking at a certain place, you can see it's a book or it's a flower or whatever. You can do object detection. But it all depends on where you're looking at. This is about the model splitting. Now I'm going to give you another general approach. It's called ensemble splitting. We know we have the first model splitting method is you're trying to allow yourself to work on a number of LLMs. For example, very expensive GPT-4 and so on. You can work on less expensive, much less expensive GPT 3.5, or you can work on even less expensive ones. But how do you know what's the least expensive model for your prompt that will give you good accuracy? Still, so that's you need to develop a prompt complexity neural net, which will quickly tell us what's the least expensive model that will give you acceptable performance. So that's a complexity net. So you have 3 nets, for example. You have a complexity net, which is a very simple network that allows you to, for a given prompt, you can pick up the least expensive model to use. To cut down the latency, it could cut down the cost. So this actually was done by some undergraduates at Harvard now. It's being developed, some companies have been formed, all this stuff. So a lot of opportunity in these areas. So you have multiple models on the infrastructure, so you can select the proper one to use for a given prompt. Next one is pretty typical thing people do with training large language model. They have a mixture of experts. So the question is that which experts you use, or which combinations of experts you use, with what kind of weighting you should use. So you train a gating thing which is similar to the complexity net that can determine how you take the outputs from the experts, how to combine them automatically to get optimal results. So this is a very powerful method as well. So all these things are happening in parallel. The models being improved, the gating networks being improved all the time. And sometimes you use multiple experts, sometimes you use one expert, and so on, in different areas. Last method, number 8. This is also some ongoing work. You have a very powerful, for example, a cloud feature extractor based on, for example, Dino. This is a self-training kind of methods. Is just don't use the classification to help you to get the features. Automatically, from an image, you can get the features of the image. It's a class-free method. This Dino is very powerful. You can get good embeddings from an image that can apply to all sorts of downstream classification tasks. So this will be great, but this model is huge. Okay, you put in a cloud. You get improved all the time. Then the cloud will spawn small models for the edge. You can go up, go down, go to middle, go down. You're spawning a whole bunch of different edge models, which are much smaller, which will work on the local data of the client. And when the local environment changes, you need to adapt. So you can tell the cloud that my class definition has changed. In that case, when there's enough changes, cloud will do the respawning, will do distillations again for all the edges. So the operation happen in all sorts of places in parallel. The cloud is doing his job, doing the distillations continuously, spawning the small models to the clients, to the edges. They are doing their own things all the time, recognize things very quickly. But when the new classes showed up, the clients would tell the cloud that you should do the distillation again to update the global embedding for everybody. Okay, so I give you this 8 methods. Okay, these are state-of-art things here. So summary, this page has the first 4 methods. Okay, these are pictures. So you can remember the next page have the next 4 methods. Conclusion. Distributed computing for AI is distributed computing, but it's really exploring things you need to do for machine learning. Distributed computing is an old field, has been around for a long time. But because now the new applications in AI, distributed computing is evolving. For example, all these splitting methods I talk about, they all relate to the AI computation. New splitting methods. And there's millions of splitting methods will coming up in the next several years. Second point is that this splitting method based on machine learning usually can allow us to do good balancing, performance balancing between accuracy, computation time, and implementation cost. The third point is that these opportunities of doing new splitting for distributed computing for AI will enrich the distributed computing technology. So we're going to drive, the AI is going to drive the distributed computing to a new level in the next several years. A lot of things will happen in this field. So AI is not just model, it's not just data. Computing, okay. Computer scientists will have a job again. Thank you very much.
Thank you so much, Professor Kong, for your compelling presentation on distributed computing for AI. Really interesting, very detailed on the new splitting methods. And for now, we really hope that this discussion or this presentation really sparks further discussion as well throughout the conference. Our next speaker is a distinguished university professor at King Fahd University of Petroleum and Minerals. He is a leading figure in electrical engineering, has over 500 publications and 23 US patents, with his research cited over 21,000 times. Today he will share insights in his talk titled Renewable Energy, Integration, Challenges and Solutions. Please join me in welcoming Professor Mohammed Abidou.
Good morning, everyone. Firstly, I would like to thank the organizers for inviting me for this chance to be with you this morning. My talk is renewable. Okay, so we can go back. Okay, renewable energy integration. Challenges and solution. Renewable energy is very wide area. You can find people in physics, people in material science. They are developing the material of the PV, for example. Here we are talking about the impact of renewable energy in power system. How to integrate, how to manage the renewable sources within the power system, how to get use of them. So we have a lot of challenges, and also we have some solutions, and we still have a long way to go for 100% green. So we will talk about the renewable energy overview, installations, and different types, and the driving force behind increasing installations of renewable energy worldwide, integration challenges, and possible solutions or potential solutions. So we used to, in early days, we used to have a very simple power system, generation, transmission, and distribution, consumers. And we have only one flow of power from generation to consumer. But recently we have some renewable energy come to the generation side, and not only generation side, but also in consumer side. We have now prosumers that can generate and sell power to the utility. So power flow now becomes like bi-directional. It's not only one directional. You can see here some inverter-based renewable energy becomes in the generation. And in future, renewable energy will dominate. This is the green lights here, green circles, and at the expense of the conventional generations. And this, of course, will come to the different renewable energy sources that we have, PV, CSP, concentrated solar power, wind, hydro, we have wave, tide, and the geothermal, and also biomass. Of course, some of them are can be integrated without any problem, like CSP, like geothermal, like biomass, hydro also, but unfortunately for the PV and wind, which is very widely dominated now, create some issues to the power systems. So just to give you a flavor of how we are going with the renewable energy, you can see in last 10 years, we have from 2.8 increase of the penetration from 2.8 of PV and wind to 12.1% in the power generation. So we have like penetration level now about approximately 30% of the electricity generation comes from renewable energy. This is up to 2022, but if we project this to the to 2050, we can have like 86% from renewable energy for electricity generation, and mainly comes from the PV and wind. PV 8.5 the terawatt, and also the wind 6.0 terawatt as installation capacity. So we expect that the PV will be like 40% or 42% of the generation, and the wind also will be like 35% of the generation in 2050. So what are the driving force behind RE? Why we are going to increase although some challenges with the renewable energy integration. What is the driving force? Driving force definitely is global warming. Electricity share about 30% of the carbon dioxide emission, and also transportation sector shares about also 27 or 30% of the carbon dioxide emissions. So if we can go for renewable, go for electrification, we can greatly reduce the carbon emission. So depending on the fossil fuel, which is currently the conventional generation, of course increase the greenhouse gases, increase the temperature, affect the society and health, human health, and also deplete the fossil fuel soon. So this is the renewable map for reduction of the emission. Comes from about 75% comes from the renewable energy and the transportation. Of course, you know, according to the Paris Climate Agreement, each country now set some targets to reduce the carbon emission or greenhouse gases. So these are the investment in 2023 for the renewable energy and electrification. You can see here like $600 billion worldwide, and also for the investment for the electrification. But this is like the amount that you can see here, which is almost double. That's needed every year in order to achieve 2030 objectives. So a lot of investments should be done to move or to shift from fossil fuel to the renewable energy and electrification. So just an example for the Kingdom of Saudi Arabia case. This is the planned renewable energy generation. In 2030, they are aiming to have like 50% of the generation comes from the renewable energy, 40 gigawatt from PV and 16 gigawatt from wind, and 2.7 from geothermal and CSB. So very ambitious objective. And actually, in Kingdom of Saudi Arabia, they set some national missions regarding the renewable energy and the net zero emission. As you can see here, in 2035, they need 50% of the electricity generation from renewable energy. They need to be like fourth largest producer of EVs, electrification objectives, and also to achieve net zero emission by 2060. Recently in the conference last year, His Excellency Ministry of Energy, Prince Abdulaziz bin Salman, mentioned that they need to install 20 gigawatt of PV every year in order to achieve, like in 2030, they need 130 gigawatt. So the question is, can we go to 100% green? If the answer is yes, but of course we have a lot of challenges to integrate these resources into power system or into utility. The challenge is simply the intermittency. This is the feature of or characteristic of the main type of main sources of renewable energy, which is a PV and wind. Also the inertia reduction. When you replace the renewable energy, you replace the conventional generation by renewable energy. In this case, we have a lot of problems in stability of the power system and the frequency regulation. The variability of the renewable energy sources, PV and wind, as you know, depends on radiation and wind speed. So if there is no wind, there is no power. So you have a lot of variability in the power. Power quality, if you replace conventional generation by inverter-based generation, you have a lot of problems. In addition to the power quality, the big issue in power system in terms of you have a lot of problems, voltage dip, voltage swell, harmonics, voltage flicker, and so on. But with the renewable energy, we add another challenge of the power quality issues. Forecasting of the renewable energy is very important, but unfortunately, still the accuracy is not as high as expected. A lot of work can be done here through the artificial intelligence. Location of the renewable energy, it is not, usually we can have like excellent sites far from the load, far from the utility grid as well. So it needs a lot of expansions and grid enhancement and so on. Protection also, protection relays are set as a power, especially for the distribution part. Power is flow in one side or one direction, but now we have two-directional power flow. So intermittency, as you know, PV is depends on irradiation. So as the radiation increases, the power output increases. And also for the wind, as you can see here, within the working range of the wind speed, above about 3 meters per second and less than 25 meters per second. So this is the working area. So the power output also depends on the wind speed. So this variability of the irradiation, you can have a cloudy day, you can have a rainy day, you can have a sunny day. So the power output is changing, and also wind speed is blowing up or no wind. So this makes the renewable energy sources are non-dispatchable. We cannot rely on these renewable sources when we go to the economic dispatch or power dispatch among the commuted generation. So you have to be careful here. So this is the typical outputs of the PV in sunny day, in cloudy day, in rainy day, and to the right you can have also the wind power output. The first one with the second per second, and the other one over the second one is over the 1 month. So you can see here some of the outputs equal to 0. So there is no wind, so no power. In inertia reduction, we have in power system generally, in the stability of the power system, we have very basic question which is the swing equation. Swing equation balance, you have to balance between the demand and the generation. So this balance makes if we have unbalance, we have a frequency deviation. We can allow for definitely very minimal margin for the frequency deviation, but if the frequency deviate high and below the bounds, you have to shed some loads. If it is greater than the upper bound, you have to shed some generators. So you have to keep the balance. And as you know, with this, as you can see here in the dF by dt, which is the rate of change of the frequency, depends on the inertia, which is h. Inversely depend on h. So if we replace the conventional generator, which have like synchronous generator with very huge rotor, very huge quantity of the kinetic energy stored in this rotor, so this kinetic energy makes like a buffer between demand and so if we have any deviation, we can take from the kinetic energy, or to the rotor will decelerate or accelerate, depends on this. But if we replace this conventional generation by inverter-based, where there is no inertia, in this case we expect that rate of change of the frequency will be high, and we can go down to lower values of the frequency with high penetration of the renewable. So if we replace this conventional generator by inverter-based PV, wind, and others, so we expect that the Rocoff or rate of change of the frequency will be higher. So you have to address this variability of the renewable sources. This is PV. As you can see here, PV can vary from one day to another, from one season to another. And you can see here a case of the California, which address the PV penetration. Usually during the noon time, the power output of the PV is high, so the net load becomes very low. But towards the end of the day, PV power will be less, and you can see here within 2 hours or 3 hours, the power system operator needs to have a reserve to cover 13 gigawatt in 1 hour or 2 hours or 3 hours. So this is very challenging, of course. Similar behavior also for the wind. You can see here from one day to another, you have a very big difference of the power output. The power quality, of course, the integration or connection of the renewable energy to the utility needs power converters. You convert from DC to AC, or from AC to DC, or whatever. So you need the power converters or the inverters everywhere in the system to connect the PV, the wind, everything. Energy storage. So the penetration of this renewable power converters are very high nowadays in the utility. So this, of course, will impose some of the challenges regarding the harmonics. Here you can see here 3 cases. Normal case, if we increase the grid impedance, you can see the waveform of the voltage and the current now becomes very distorted, and you can even go to resonance in the 3rd case if the impedance of the grid is high. And forecasting is usually in power system we used to have like load forecasting or demand forecasting. So we have only one source of uncertainty. But nowadays with the electric vehicle as a new load, also this imposes some challenge in forecasting. And as we listened yesterday with Dr. Daniel in his talk, in EV also a stochastic process, so you cannot expect how many cars will be plugged in. So this also gives an error in the forecasting. And nowadays, the error is also in generation side. The forecasting error also in generation side if you have PV and wind. Weather-dependent generation is the main source of forecasting error as a PV and wind. So this, you can see here like just a very study case. During the 1 week, you can have the actual to the left, actual and the predicted, and to the right you have the error. And you can see here the error can go up to 3.6 gigawatt, the error in forecasting. So this is very challenging. This, for the power system operator, you have to have a reserve to cover this amount of power, which is very challenging. Location of the PV and wind can be anywhere, depends on the weather conditions. So you need to have like transmission system expansion, enhancing the grid at these locations. So this is also another. The protection we use we used to have like one way of power in distribution part, and this was very easy for overcurrent relays to do. But nowadays, if we have two-way of power, so two-way of the power, in this case, we have to revisit the protection principles. We have to maybe rely on adaptive protection or so. As you can see here, if we have a fault, this fault, if there is no renewable energy, the relay will be set and work properly. But if we have renewable energy, now the current contribution from the utility to the fault becomes less, and we may lose the sensitivity or the selectivity of the relays. So what are the potential solutions to address or to mitigate these challenges? One of the enabling technology is the energy storage. If we can have energy storage with different types of energy storage, pumped hydro, we have hydrogen, batteries, supercapacitors, superconducting magnetic energy storage, and others. If we have such energy storage systems, this will increase the penetration of the renewable energy, will reduce the variability, and also will reduce the curtailment of the renewables. In terms of virtual inertia, we can have like a grid forming inverters rather than, we used to have grid following. So the grid following inverters where the grid is responsible for the frequency and the voltage. But nowadays we can have like a virtual inertia or emulated inertia or synthetic inertia through the power inverters. We can use also synchronous condensers to provide inertia for decreasing the rate of change of the frequency. We can use also the derating the wind and PV generation, which is not, of course, recommended. That means you are curtailing the power. There is power, but you cannot use of it. So another solution for the increasing the penetration of the renewable energy is the demand response. If you can control the load, if you can reduce or increase the load, depends on the status of the renewable energy generation, you can allow for more penetration of renewable energy. You can shift some loads. We have some shiftable loads even in our houses. You can shift some loads, dryer, washing machine, you can change the time, and also you can valley filling. You can store the energy whenever you have low price or high generation, and you can discharge it later. So you can do some demand response to increase the penetration of the another way to smooth the output of the renewable energy, you can use energy storage, as we mentioned, supercapacitors. Here we use it in our lab with the RTDS. We simulate the power change, PV output change, increase, so we can charge the supercapacitor, and the supercapacitor can discharge if we have shortage in generation. So we can keep the power injected to the utility constant. So grid enhancement, a lot of grid enhancement also can be done in order to increase the penetration level. Grid interconnections among the countries, among the utilities, this will help in increasing the penetration of the renewable energy. Expansion, transmission expansion, FACS devices, flexible AC transmission system devices that can control the voltage, control the power power flow. So this is also, wide area measurements also will help in monitoring and protection and control. Diversity of renewable energy sources in terms of types. You can, diverse from PV and wind, and also from sites. Virtual power lines also is another solution to relieve the overloading of a transmission line by adding the energy storage system, so you can charge and discharge depends on this. Artificial intelligence applications is a hot area in this to overcome the challenges. Optimal location, design, sizing, more accurate forecasting, effective controllers, energy management, data analytics, fault detection, classification, battery management system. All these are possible applications for the artificial intelligence. In adaptive protection, we have to change the principles of the protection relays. Adaptive protection depends on the topology, whether you have the microgrid islanded mode or in grid connected mode. So this is also one way to solve these challenges. Other also possible solutions is to integrate the energy systems. You can integrate the power infrastructure with the gas infrastructure. With the renewable energy, you can have electrolyzers to produce hydrogen. Hydrogen can be pumped to the gas infrastructure or can be used also with the fuel cells to generate power whenever needed. So such integration will help in increasing the penetration of renewable energy in the power system. Of course, you can increase also the flexibility in terms of electrification, in terms of decentralization of the power system through distributed energy resources, microgrids, and others, and digitalization also, as we have yesterday panel discussion about the digitalization. It's very, very important issue. So in conclusion, the transition towards all renewable has a lot of changes, and many government and business are investing in technologies that harness the energy all around us. Hopefully we can, with more research and more technology innovation, we can mitigate the challenges and reach to a high level of penetration of renewable energy. Thank you.
Thank you, Professor Mohammed, for this enlightening talk on renewable energy integration challenges and possible solutions for and aspects for sustainable energy development. We truly appreciate your valuable contribution. Before we proceed to our next session, we would be taking a brief break for refreshments and networking back in the multi-purpose hall, and we will reconvene at 10:50 with an exciting session with our next keynote speaker. Enjoy your coffee.
بقول لك ماستريكا يلا
Welcome back, everyone. I hope you enjoyed your break and had the opportunity to connect with your fellow attendees and have some great conversations. Let's bring our refreshed minds and renewed energy back to the room. Our next keynote speaker is a professor from the University of Alberta in Edmonton, famously known as the City of Champions. Professor Jamaluddin embodies the spirit of excellence and innovation that this title conveys. And Professor Jamaluddin has received the Alberta Science and Technology Leadership Award for Innovation, and he directs the Water Research Center. Please welcome Professor Mohammed Jamaluddin.
Okay, assalamu alaikum. Good morning, everyone. Thanks for having me here today. My talk today will be a bit different than the previous keynote speeches or presentations. We'll have a gear shift here a little bit towards more like environmental applications, but from a sustainability point of view. So I'll be talking to you today about how can we deal with municipal wastewater or even industrial wastewater that might contain a lot of pollutants that will have an impact on the environment, harmful impact or adverse impact, and how can we deal with that, especially in a place like Oman where water could be scarce as a resource. So I'll talk today about a few things, micropollutants or contaminants. How can we deal with them? I'll start with a very famous approach of dealing with these contaminants. I am not sure if they have it here in Oman. I'm pretty sure they have it somewhere in Oman, but it requires a lot of actually energy, a lot of power, and it's actually very, very, very expensive process, very intensive when it comes to labor, operation, maintenance, and whatnot. And it does work sometimes, but then I will shift the gear from there and show you other approaches that very doable nowadays, very sustainable, can depend on solar energy and so on. And then I'll finish with some future perspectives. So for example, if I look at my current research now, actually I started doing my research at U of A in 2001. And I started working on, processes like advanced oxidation, ozone, membrane treatments. I'm sure here in Oman you are very familiar with membrane treatment for desalination to produce drinking water quality. And all these processes require a lot of energy, a lot of power, basically. So this is something that I started working on. And then a few years later, I shifted gear to green approaches, green chemistry. And all over the research areas I've been working on, we always deal with micropollutants or contaminants that could have actually negative impact on the environment if released to the environment. So this is basically, at a high level, the focus of my research. And I do apologize if my presentation will be more on the technical side. I will try to dilute it a little bit because I know it's a very diverse background of audience here. So, but I do apologize if it's highly technical. It's not actually. So what are these micropollutants? Micropollutants, they could exist in our wastewater at, like micro level, microgram per liter, or even picogram per liter, nanogram per liter, very low levels. And these micropollutants actually come from a variety of sources. They could be some pesticides we use, pharmaceuticals, like you take a drug, like I took this morning, 2 tablets of Advil. Not all the dose will be used. Some of it will go out, excreted, then this end up in the wastewater, and so on and so forth. It could be also like personal care products. We have a lot of use of it nowadays, like steroidal hormones, like industrial chemicals, chemical industry, and so on. Surfactants, many compounds. All of these pollutants end up in the wastewater. And this wastewater goes to a treatment facility. In Oman here, for example, you have secondary treatment level. I have seen all these pipes going in the gardens, irrigating the gardens and trees using municipally treated or secondary treated effluent. So I guarantee you 70% or 80%, sometimes 95% of some of the micropollutants are there. So it goes to the soil. Some of it is retained by the soil. Some of it will actually be transported all the way or migrated all the way to your groundwater system. And they keep coming back to us. So actually it's something that we have to develop standards, especially for reuse of the water like in Oman here, so you can have a safe actually reuse of the water. Some of them actually, if you use them like these municipally treated effluents for irrigating crops, even after some advanced treatment, you need to make sure these irrigation waters are free of these pollutants. So that's why we're focusing a lot on this nowadays. In Canada, I don't know if you're aware of this or not, I think we have, if I'm not mistaken, in Alberta specifically, we have the second oil reserves in the world after Saudi Arabia, but it's an unconventional oil. We call it oil sands. So a lot of my work has been focusing on gas industry, oil and gas industry there, to produce water. And again, this is another big problem here in Oman. So it's something that needs to be addressed. This produced water, what do you do with it? Because it has also a lot of nasty compounds that are highly toxic and the environment, even to humans and aquatic life and so on. Okay. So examples of, don't worry about the structure, structure of the compounds. So some of the compounds actually include, these two compounds here. So this is actually a compound, DPG, and the other one is actually 6-PPD quinone. These two specific compounds, you know where they come from? Tires. Tires wearing off. So these compounds end up in the environment, and they are highly persistent and very hard to degrade, highly toxic. They even found these compounds in the northern polar waters. So they could actually migrate and end up in, very far away, environments where people use no tires there, but they can migrate in the environment quite a bit. So with the weather here in Oman, very hot in the summer, so the wearing off of these tires will be a lot faster, and then you have them in the wastewater, because they could be in the surface runoff or washed away with rain and end up in the wastewater, so these compounds are highly toxic and persistent. So we're working on some of these compounds nowadays. Another example is actually these 3 pharmaceuticals. And we keep those pharmaceuticals for personal care products. Every once in a while, you have new compounds emerging. So we always look at those emerging compounds, because usually the emerging compounds, we don't have experience in dealing with them or how to treat them, remove them from water or wastewater. So we are always working with these compounds. I don't know if anybody here has environmental background or even non-environmental background. If you read the news, these compounds here, per and polyfluoroalkyl substances or PFAS compounds, they come from many, many different sources. These are fire retardant compounds used in some clothing for fire-resistant compounds. When you actually, they come actually also from some plastics. They come from many, many sources. And these compounds, they are super, super resistant and very hard. Even some of the most advanced treatments out there, they cannot be degraded by them. So it's actually a major issue now in everywhere. US EPA has added them to the list of the priority pollutants, and the only way to take them out is physically remove them or absorb them and then remove them. But then once you remove them on absorption-based materials or adsorbents, you still have to deal with them. So they are highly persistent. And a lot of them actually, there's a big list of them. These examples, those 2 examples, these are the ones are the most common. And some of those compounds have been actually banned from being used now in different places around the world. So these compounds are highly persistent, highly toxic, and so on. So these are just very few examples that we're currently working on, and many people are working on them when it comes to water and wastewater treatment. So I'll just give you some snapshots of some of the work we have been working on. So this is an example of actually one of my previous students. We wanted to work on some of these compounds I showed you using two different common approaches known worldwide when it comes to treatment. Ozone and actually activated carbon. Ozone is a highly oxidant, very super strong oxidant used worldwide to basically degrade a lot of organics, disinfecting the water and so on. But again, when you use ozone, it's very expensive, requires a lot of energy to generate on site. And once you use it by law, even if you know that you can prove it and you know that it's all utilized, all used up, by law, you have to cap all your reactors, collect all the off-gas, take it to a destruction facility, working 24/7. And even if you know that for sure, 200% there is no ozone in the off-gas, you still by law have to do that. And the gas that's being destructed, it has to be emitted to the atmosphere at a certain height above the ground, again for safety precautions. So it's a very expensive process and requires a lot of energy to generate that ozone gas on site for treatment. Like for example, in Canada and US, ozone is used all over the world. All over the cities, especially in US, for disinfecting water, treating municipal wastewater, industrial wastewater. And again, expensive process, requires a lot of energy. Just keep that in mind. So in this study here, we used ozone and we coupled ozone with activated carbon to treat some of these organics. Okay? And one thing I should pay attention, in our field of environmental engineering, it's not a one-man show. It's actually a multidisciplinary approach. We work with people from biological sciences, from chemistry, sometimes from pharmaceutical, actually pharmacy. It depends on, the scope of the work. So in this study here, we actually used a mixture of a lot of these compounds, pharmaceuticals, herbicides, and those two examples of the PFAS compounds at the bottom there. So we made a mixture of all these pollutants in a water, basically sample. And in this system here, basically we had those 17 micropollutants. We spiked them and we looked at how can we use ozone coupled with powder activated carbon for actually advancing the degradation of these pollutants. And we use one of the techniques here, electron paramagnetic resonance spectroscopic approach. This actually was a unit that's in the pharmacy department. And this is where we collaborated with them in measuring in situ or in place to prove that we are forming these highly reactive oxidants or radical species that could actually be targeting these compounds. So we did go to the lab, we made the sample. In this sample, we added ozone and powder activated carbon. We used some residence time to make sure the treatment is done. And then we analyze the sample for analyzing for any remaining ozone, how much we utilize out of this treatment. And then we go to the lab. Basically in the lab there, as you can see, these are, highly sensitive analytical equipment that we use to analyze for these micropollutants to a very specific, to a very low level in the lab. So if you're working in an environmental field, you need to make sure you have access to these highly sensitive analytical equipment. Otherwise, this will be your bottleneck. But we are lucky at University of Alberta and my labs, we have actually access to all these analytical equipment. So we analyze the samples, and then we go to the pharmacy. We recreate the experiment again in pharmacy, where we actually, with the PER technique, we can measure in real time the formation of these chemicals to make sure that they are actually being formed to degrade these compounds. And then, we generated, this curve here. This curve here, without going into the technical details, on the x-axis, the amount of powder activated carbon we add. And for each point, we estimated basically the initial ozone demand. What does it mean when you add something to the water? In terms of ozone, there is an initial demand. You satisfy immediately, and after that, you need to add more than that demand so you can satisfy your own needs in terms of the treatment. So we can see that actually we can have a good estimation of the demand, initial demand, so we can always know at certain ozone dose, a certain powder activated carbon dose, we need to have this much of ozone added above the demand so we can do the treatment or achieve the treatment level needed. So we can actually forecast that very well. And then when we wanted to look into now how fast the treatment process can happen when we add the powder activated carbon and we add the ozone. So how fast this treatment process can happen. And we added here only 10 milligram per liter of ozone, and that's a typical dose added to wastewater. In many facilities in North America, they add that ozone dose, okay? 10 milligrams per liter. And we found that at different doses of the powder activated carbon added, the process is quite fast, but only up to a certain limit here, about 100 milligram per liter. After that, it slows down. This means, like you should only target this initial phase, because actually it's quite fast process. You can degrade the compounds very easily and very fast. And fast means your reactor or your treatment system or vessel, its size could be small. The residence time needed is small. You don't have to oversize it, because oversizing things means expensive. Okay, so this means we have to target the initial region of the treatment. So that's good to know. And then when we look at the different compounds and their percentage removal using actually either catalytic ozone, means ozone and powder activated carbon at 100 milligram per liter carbon, with 10 ozone, 10 milligram per liter, that's the upper limit. That's the light blue. And then the yellow is the ozone, 10 milligram per liter and only 25 milligram per liter pack. As you can see, a lot of these compounds, 25 milligram per liter powder activated carbon is just enough. You don't need to go above that. But for some of the compounds, it's not enough. Like some of these compounds here, you need to go to a higher level of powder activated carbon. But guess what? For these two compounds, you need the high level of carbon. And that's not because of ozone. Ozone is not doing much here. The removal is happening mostly because of the absorption. So these compounds, if you remember, the ones I told you, they are highly toxic now. They are on the list of the US EPA. These surfactants type structures or PFAS compounds, they are quite persistent to even the most advanced treatment system used worldwide when it comes to wastewater. That means it's very alarming, actually. Okay? And this is another thing when we used specifically for each compound in terms of the time and the treatment. A lot of them, they could be degraded within the first minute, which means you don't need a big sized reactor. You might need a small pipe. You add the ozone. If you have a highly efficient system to transfer the ozone from the gas phase into the liquid or into water or wastewater, you only need 1 minute. So you don't need, again, to supersize it. There are lots of companies out there that develop actually small innovative reactors where you add ozone very quickly and it's reaching the treatment target within minutes, actually, or seconds. And some of them are degraded faster than others, but usually within a minute they are degraded, actually. But those two, again, specific compounds, the PFAS compounds, as you can see from those two curves here, or two sets of curves, the main removal is because of the absorption. Absorption, basically, guys, is a physical treatment. Like in your fridge, you might have those filters there. They are an absorption type filters. Or sometimes if you live in a country where the water is not that safe, you add an absorption system, basically connected to your tap, so the water comes out of the tap. Some of the contaminants are absorbed. And over time, this absorption column is overloaded or exhausted, so you have to replace it because it's a physical process. You don't get rid of the compounds by chemical reaction, so they are degraded. You physically remove them from one medium to another. So that's the problem with absorption systems, is that eventually you need to deal with them because you will remove them from the water into a solid phase. So what do you do with the solid phase? So it becomes a management nightmare, right? But again, this is something that only currently works for these compounds. There is a lot of research being done for these compounds using other approaches. So this is what we got here. So in terms of the catalytic effect, the word catalysis, it's in chemical reactions, you add a catalyst to make the reaction a lot faster, so it's more efficient. So the catalytic effect here happened because of adding the powder activated carbon, the pack. So it was actually quite good for all the compounds except for those two, the PFAS compounds, okay? But again, that actually is proven also by this PR or EPR, technique. And we were able to actually, in this technique, we used basically a trapping agent. So we can measure in situ the formation of these radicals or the chemical compounds that they act as superoxidants. And we've proved that these compounds are generated at a higher rate in the presence of ozone and powder activated carbon together. If you have ozone only, you don't generate as much. So we have proven that by that technique. Okay? And then this is the mechanism we actually proposed in terms of the degradation, that these radicals, OH dot, or these chemicals or oxidants, they are generated on the surface of the adsorbent, and once they are generated, immediately they are reacted right away with the compounds. So they are generated and react immediately. So you can have a continuous supply of them, okay? Another study now, we said, okay, let's shift gear from ozone. You need a lot of power to generate it on site and so on. What about solar-driven photocatalysis? So in Canada, we are trying to use that, although sunlight is not as much as here. The days are sometimes shorter, and the weather also is quite prohibitive, but we're trying to look into other sustainable approaches of treatment. So this is something in Oman here will be greatly actually utilized if there is interest in that. So here we are working on actually this catalyst, the G3C3 and 4 here, to degrade that specific compound I mentioned to you, that compound that leaches out of tires, okay, rubber tires. Okay, and we investigated, like how can we make it, the process of making it, and also like doping it with some potassium to make it a more efficient treatment. So here we can actually, we used actually a pure chemical, urea, but actually it could be used if you have a separate actually like plumbing system. If you can collect separately urine and you can extract urea out of it, so it becomes kind of like a circular economy approach, or you can value add a product out of your waste. And from there, you can actually use this actually to make that catalyst, which is graphitic carbon nitride catalyst. And the way we make that catalyst, we synthesize it in a way that it could actually absorb sunlight. So it gets actually, once absorb the sunlight, then it can generate those chemicals. Instead of using ozone, we depend on the solar light for that, okay? So this is a process of making it, and basically this material is very stable, like even under high temperatures, 600 degrees Celsius, quite stable. It's easy to use and transport, and also a simple process to make. And by making that catalyst, we were also able to reduce the band gap. So by reducing the band gap, so we can absorb more sunlight. And that's another schematic, how can we make it? So we make this heterostructure, and then we can actually engineer it this in an easy way in the lab, and by doing elemental doping here. Namely, we tried different things, but we ended up with potassium is the best one. And but you can do also other dopings, adding other things, to it. But basically, by doing that synthesis process, we were able to utilize the heterojunction there to reduce the band gap, but also with the potassium being doped there as a trace element, we enhance the photocatalytic ability or efficiency of that system. And that's a compound, that's the chemical structure of the compound we are targeting here. And as I told you earlier, this compound can be persist in the environment for a long time and long distance, can travel, and also have a very toxic impact on humans and other living creatures like rats, and even a lot of studies now being done to look at their impact on wildlife or fish and so on. So when you look at that compound, when we try to basically with the treatment using the catalyst without the potassium doping, you can see the blue line here, but with the potassium doping, we can degrade it almost to 100% within only 6 hours. And that's using sunlight. So that's something very efficient, could be utilized in places like Oman very easily. And it's an actually passive treatment system, green approach. You don't have to generate electricity, to generate ozone, and so on and so forth. And the right side figure there showed that the reaction rate So we always, as engineers, we like to determine the reaction rates. So from the reaction rates, we know how fast the process is, so you can size your reactor accordingly, okay? So it's quite fast process. And when we looked at basically, we looked at the previous one, just model compound, to see, yes, it works. So we take that compound and we spike it in a secondary effluent, similar to what you do here in Oman, to treat all your gardens, a lot of your, I don't know, maybe crops, I don't know. But as you can see, within almost 6 hours, again, everything is degraded. So this process could be done easily in an open pond where you have enough time, enough mixing. And with that catalyst in place, within 6 hours, you degrade one of the most toxic and hard to degrade micropollutants. So this means it could be done for other micropollutants. So you can apply that here in Oman very easily. With a passive system like that, you can have a much safer, actually, water to be reused for irrigation. And to conclude for that study, that actually catalyst proved to be quite efficient. And with the synthesis approach we did, we reduced the band gap. Reducing the band gap means you can actually absorb more sunlight and becomes more efficient catalyst. So, and we were able to actually degrade that compound efficiently, and we even, using our analytical environmental chemistry approaches, we were able to detect the byproducts, and we made sure the byproducts are not toxic as the parent compound. So another study, we looked also at actually something called engineered biochar. So what that is, biochar is kind of a sort of activated carbon, but it comes from biological sources. So in this biochar case, we made it out of a very usual source of waste. We have it in Canada, in US, in Oman, in Qatar, everywhere. Every day you wake up, you go to the washroom, you wash, use the toilet, whatever, you generate wastewater. Wastewater comes from a variety of entry points into the municipal wastewater collection system. You take that wastewater, it goes to the wastewater treatment facility, it's treated, we generate sludge. That sludge, in many places, it's used as for composting to make actually a fertilizer or a compost to use for actually making like a soil amendment or whatever you want to call it, right? But it has a lot of nasty compounds in it. A lot of them are still there. So it's, in my opinion, it's quite unsafe way of dealing with our sludge. So in many places, they are moving away completely from using compost because it still has a lot of those micropollutants there, not removed completely, right? So here we made from that sludge biochar, a partially activated carbon. And then we use that biochar, actually, okay, and as actually a support media for another catalyst, bismuth tungstate. And so a material, that biochar came from waste, added to it a catalyst, then we use that approach, again, to absorb sunlight, to have in situ catalysis, okay? So again, this could be easily done here in Oman because you have the sludge, and I believe one of my colleagues here, Dr. Abdul Rahim, who invited me here, he's working on actually making biosludge out of similar waste products here. So, but you can just add to it that catalyst, then you can use actually a lot more treatment out of it, okay? And then, so in this study here, we use that catalyst to degrade that other compound, the VPG compound, that also coming from wearing off of the tires, okay? And my student used that compound to be degraded using actually here, as you can see here, the photolysis, only when you have the sunlight. That's a control, nothing is happening, nothing much. When here you have actually the bismuth tungstate alone. It can do some treatment, almost insignificant, almost no change. But when you start to add it to basically the biochar in different doses, you can see a lot of changes happening here. If you look at the light curve here, so this is where we achieved very good removal very quickly within only 4 hours. That's very actually significant. And this is the concentration of the biochars we use here. So you can go from 0 into 140. You can achieve different rates. So you can actually engineer it in a way that, depending on the size of the reactor or the pond you want to have it in, you can actually do it in different ways depending on how much biochar you add. And when we convert it into rates, then it's quite fast process and it could be achieving the target within reasonably very short time. And again, we also use this technique to prove that we are actually generating these signals here indicate that we are generating this superoxide radical species being generated on in situ. So we prove that actually this process works, and this is specifically the chemical we are generating that's causing that actually the reaction. And again, we always work with model compound to make sure it works, and then we go into the real situation. When we spike that in a real wastewater, again, it works really well. Here is untreated effluent, here is treated effluent at different doses, and so on. So it works also with the real wastewater. So we proved that it's quite actually a reasonable process that we should be taking into account. And in conclusion, it worked really well. Again, making biochar it's a value-added product out of a waste material, so circular economy approach, using a catalytic process like that, depending on solar light, so it's a green approach of treating our effluents, targeting the most harmful compounds or pollutants. Then I'll show you something quite innovative, actually very nice. I collaborated in this study here with Professor Shahua Chang, a lady in chemical engineering. She is specialized in soft matter. And we had actually a PhD student co-supervised by the two of us, where we made surface micro lenses for even not just absorbing the sunlight, but concentrating the sunlight at specific local points. So you have higher sunlight intensity, like when I was growing up in Egypt a long time ago. Like we used to have actually magnifying glasses in order to, do some etching or writing on wood, write our names and so on. So it's the same approach, right? So you actually concentrate the sunlight using those micro lenses at specific points. So you maximize the sunlight intensity and you increase the temperature, of course. So that makes the reaction even a lot faster. And this was also published in actually an ICIESTR author. It's a highly prestigious journal, actually. So these are different applications of micro lenses. You can actually use it to actually, in solar cell, to have larger photo current, or in OLED, to have better light extraction. Or you can also use it for desalination, okay? I don't know if you use it here in Oman for desalination or not, but they are being tried in different places in order to actually enhance the desalination process using this photothermal impact, because it has a stronger, it can have that impact there. Or in our application here, we're trying to target higher reaction rates or increasing the efficiency and the speed of the reactions. So we made those micro lenses in the lab. This more or less was a proof of concept. Actually, we applied for a US patent and we're waiting for finalization of that patent. And actually, we were able to make it in the lab either in a random arrangement like that or in an array. And we tested it using those two different approaches in a reactor, and did work actually quite well, even to the point where we were able to actually put them on bottles, like even plastic bottles, outside the bottles. And these bottles, let's say you are in a developing nation or a small village, you can actually fill those water bottles with water there, maybe half full or 2/3 full, and you can place them under the sun for quite a few hours. Then you can have disinfection of the water, so it's safe to drink, especially in places under severe weather conditions, or in war, like in Gaza and places like that, right? So people can depend on safe water supply even in catastrophic events. Okay, so I'm not going to bother you with the details, but actually we looked at these micro lenses, the geometrical properties, their optical properties and so on. And we were able to actually make them really well. And we even actually simulated their formation with another professor in electrical engineering who did the simulations of their formation and so on. And we predicted their formation very well. And when we looked at actually as a proof of concept, how can it be used for degrading micro pollutants, we actually proved that can work. This was actually a very simple compound people use out there, methylene blue. Actually, this is the compound we use, if I'm not mistaken, and it proved that it can work quite well, and we even, I think this methylene orange, sorry, and we predicted that for the degradation of it and even the byproducts, and we measured the byproducts based on that reaction pathway, and it was proven to work quite well. The same mechanism works when we use ozone or like engineered systems. So this means it could work actually quite well. And these are only micro lenses. So the next generation, and these are the simulations that they were done actually by our colleague in electrical engineering, and we proved that there is an effect of the focus effect of the sunlight of these micro lenses. So methylene orange is a weak compound. It's a proof of concept. So we pushed this to the next level, and we published the work as well, where we targeted compounds, micropollutants. And not only that, on these micro lenses, we are now adding to their surface catalysts. The catalysts I showed you, but instead of being on biochar, on the previous study, we are putting those catalysts now on these micro lenses, so we can enhance even the degradation a lot faster. Okay, so this is actually a nice way of doing treatment using actually sustainable source of energy, sunlight, and you have plenty of that here, so it could be used all year long, like around, and this could be quite efficient approach, green approach, except from the process of making those PDMS-based, micro lenses, and you can have them on surfaces, sheets, you can make them on different surfaces, and we did them on curved surfaces, flat surfaces, and you could be using that very efficiently in Oman here to degrade micropollutants, treat your water, even disinfect the water to kill pathogens. If you have areas, like some localities here where they don't have access to nice, highly innovative engineered systems for disinfection to kill the pathogens, so people don't get sick of water that might have, bacteria or viruses and so on. So it's a very nice approach of doing treatment, either in developed areas or underdeveloped areas. Thank you very much. Oh, I forgot. Future perspectives. Just in my opinion, we should depend actually on these things going forward as much as we can. So don't look always for the fancy treatment system that require a lot of energy, a lot of manpower, capital power. With some innovation, we can do a lot of things using sustainable energy, and there is a future for us to continue going into the future and utilizing as much as we can of our resources, from waste to value-added products, and sources of energy that are in abundance here. So make sure that you always encourage innovation in the treatments and in the way we do things, not just we go with the flow, whatever we're used to, we keep doing the same thing. We should change how we make things. Thank you very much, and I'd like to acknowledge the support. We always get support from industry to support our work, and this is how we actually drive innovation, with their support, financial support, interaction with industry, to make sure we always meet their demands and needs by doing that research. Okay, thank you.
Thank you, Professor Mohammed, for that really interesting topic, very interesting presentation, and for making complex topic like this as clear as purified water. And now it is with great pleasure that I introduce Dr. Catalina Lacerna, who will be leading our workshop titled The Evolution from Oral Traditions to Cyber Societies. Dr. Lacerna is a research fellow at Harvard Berkman Center and a senior fellow at Harvard X, and she has conducted policy research on distance education and directed the Masters of Liberal Arts in Technologies of Education at Harvard Extension School. Let's give a round of applause to Dr. Catalina Lacerna.
Greetings, everyone. And now for something completely different. I am delighted to be here and to tell you about my research interests. As you can see from my biography, I come from a country in South America, Colombia. Colombian borders Venezuela, Peru, Ecuador, and Panama. I'm going to begin by speaking first about my doctoral field work, which I conducted primarily in the south of Colombia, a place called San Juan. Here I was looking at how children in a peasant village unfolds and how it contrasts with the way learning happens in school. I wanted to look at how learning happens and when there was activities that have economic value where mistakes have monetary consequences. So when you make a mistake in a chore, there's a real consequence. When you do a mistake in a academic topic, there's something different. It's a different kind of economy, if you like. Next slide. In San Juan, where I did my field work, many families have cows that produce milk, and the children are taught to help their parents, though the process is called peripheral legitimate participation. In other words, it's not a mock activity, it's a real thing, and parents teach how to milk the cows and how to make cheese. So whenever you see children working and you see them with their parents, they are learning by doing. The adults create variations in the routine to enable the child to participate as various activities. So next slide. I literally went to the field with families to examine the sociological point of view, what they were learning meant for the various participants. I discovered work routines have many subroutines, and the children become expert at certain subroutines, relating and contributing authentically to the activity. The children participate in such a way that that is truly important. They have a certain critical role to play, and mistakes have consequences. The parents start to perform their routine, for example, milking, and find a place in which the child can take over the activity with the adults. The learning for the children has both engaging and deeply rewarding aspects because they can see that what they have been producing and there was a real social acceptance of their role. These are authentic activities, not simulations. That is a very important feature, the curriculum to which there is a curriculum that you cannot fail. The parents adapt the routine so that the children can participate. And the next slide. In contrast, when you go to the school, we have found very different environment. What the children are learning was literacy and numeracy. Aside from learning the mechanics of reading, writing, and arithmetic, there are also lessons having to do with biology, mathematics, etc. What I actually saw from those lessons was that the division of labor was rather different from what happens in the chore curriculum. The routine were not repeated. Instead, the teacher would plow through material as they received from the Ministry of Education. And students would be expected to memorize these things. Very often, the students could not understand the concepts, nor relate to them to their everyday lives. Here I'm interested into contrasting in San Juan, where the local traditions of healers, but in school, they spoke of medical practices. So they were like the traditional healers, and now they have the like mainstream practices for medical situations. So what they're being taught in school does not really make sense in the local context. In school, the only possible solution is rote memorization. So, which the children performed in order to get good grades and to graduate. Teachers had very verbal routines in which they would say things like microbes or subtrahend or minuend. and the students were expected to repeat these words and these phrases. How do you solve problems when knowledge is decontextualized? How do you cope with all of this? In tasks in everyday life, a child can be very capable and learns gradually. They repeat their routines, and what changes is not what they're doing, but their participation in that routine. I have left behind the dialogue, which Socrates considered to be really important for the development of mind. And I also did field work in a place called Limones. It was very similar study to the Pacific Coast. It was a very small village in the Pacific Coast, and as an Afro-American fisherman village. The pattern was the same. The students were very engaged in activities, what I call the chore curriculum, and were able to participate with the parents in activities such as fishing. Here, you can see the children participating in religious processions. And next one. We are all apprentices. Next one. As you can see, my father was an amateur bullfighter, and he gave me lessons. And as you can see, he was giving me the cape, and he was like pretending to be the bull. How do some of us end up as teachers, lawyers, and engineers? Probably because they knew someone who did these professions and they wanted to be like them. Maybe they are mentored or able to participate in these professional activities. That is how they learn. So I thought I would share something about myself. This is the bullfighting. I was also an apprentice, and at the time when people my age were cramming for the SATs and college entrance exams, I was doing an apprenticeship in bullfighting. Because my father was an amateur bullfighter, and we raised bullfighting cattle in our ranch. So, when there were a number of opportunities where my father would let me participate, he would, there was always somebody there, like just in case something happened, they would just run in and frighten the bull or something. Unfortunately, next slide. Yeah, the next slide. Oh, isn't there one where I'm caught? That one. Unfortunately, sometimes I was caught by the bull. I mean, it's a cow, really. So you learn from your mistakes. Actually, these are cows, and this explains why, because the bulls you cannot test. I mean, the bulls, but the cows you want to test them to see if they are, in other words, if they really go for the cape, and then you have different kinds of, you classify them in the very good ones, the mediocre ones, and the not good ones. So the way you do that, you actually have to test them. And because these were small cows, I always like to experiment with that. I wanted to see if the mothers were brave and fierce to begin learning by doing. I left this behind. Anyway, next slide. Anyway, bullfighting is something I left behind, and now instead I do swimming with horses. And that's it. Any question? Oh, sorry. No. Oh, to summarize. Sorry, I have to say something. To summarize, in the next slide. Is the next slide? Oh, yeah, okay. To summarize, I want to say something. Many of these things we learned did not involve reading or writing. There's a lot of learning that takes place without through participation and through oral conversation. In oral societies, the passing of knowledge from one generation to the next is critical. The farmer who milks cannot not have children that learn to milk. The fisherman cannot afford not to have children who learn to fish. There is a societal need for the subsistence economy that is addressed through apprenticeship. It was extremely revealing to me. In contrast, the literacy I saw in many of these peasants' children go through is where one can tell that they they were trying to recite these things by memory. They tried to memorize it and then recite them. I had great conversations with children after school about milking, about fishing, but when the conversation changed to things that they had learned in school, they just recited what they had heard and had no understanding of these concepts because they were brought from Bogota, and this was a very marginal community. The students would simply try to repeat what the teachers had said. This variety of teachings would not open up the mind, but limit it. If you think about peasant society, there is the premise that education is the way out of poverty, that this way of learning seems tragic to me. Next slide. Socrates wrote about literacy. It weakens the mind, revealing it of works that makes us strong. It's an inhumane thing. Socrates believed that writing was not an effective means of communicating knowledge. To him, face-to-face communication was the only way one person could transmit knowledge to another. Socrates taught that literacy was an enormous danger because it weakened the mind. Socrates was very worried that the increased use of books in educations would have the effect of running through students' abilities to memorize things and only remember only remember this now how Plato wrote it down. So the question is, how do you get students to actually engage in learning? This is the quest I have wanted to do in my professional research. Next slide. I was very fortunate that after field work and writing my dissertations, I landed a job in a high-tech firm called Bolt, Beranek and Newman, or BBN, which...
Just go to your magnifying glass and put all these. I guess it's a put on. It's too.
Oh, thank you. After finishing my fieldwork and writing my dissertation, I was lucky to land a job in a high-tech firm called Bolt, Beranek and Newman, or BBN, which was developing simulations for teaching subjects like genetics in the local schools. When I got there and told them how troubled I was of seeing how poor peasant children were being taught, and said, "Don't worry, we have the answer, learning through software simulations." By the way, some of you might have recognized BBN as the place where the first email message was sent. Ray Tomlinson, a computer engineer at BBN, sent the first message across the ARPANET back in 1971. The message was sent from the Digital Equipment Corporation, PDP, 10 computers to another. The message separated the user's name from the machine. And that's where the @ sign comes from, which is how commonly used in email addresses. Here's an excerpt from a student learning with GenScope simulation. It was a multi-level simulation. It means you can learn a very complicated biological system from mutations at the gene level and how this then is understood in terms of the evolution of the species. You start by tinkering with chromosomes, learning about dominant and recessive genes, zygotes at the pedigree level, and what we called the making babies, which means reproducing. Dragons, they have names. The males are dominant, and the genetic and sociological explanations very often had to do with sort of a misunderstanding of what the process was. Then there comes a software. Next slide. Is there a next slide? Do you have a next slide for this or no? Oh. Sorry? It's what? Well, I was going to talk, oh, okay. So Genscope is a software of all kinds of interesting details that can make fun or a game like dragons and make noises. You see children make dragons with names of people they knew. For example, when having horns was a recessive gene in El Salvador, I spoke with a group of teachers who had the wrong cultural assumption that framed the analysis. They thought that because male had horns, the children would, of course, male-dominated. Biologically, this is incorrect. We started to identify a lot of misconceptions people had about dominance, about inheritance, about genes, etc. So, that was a very refreshing experience for me. As you can see from this excerpt of some Hispanic children from immigrant parents using Genscope software. These students came from non-literate tradition. Even though there were a lot of tinkering, there is no sound to that? Oh, there is no sound, okay. Even though they had a very lot of tinkering with the software, they were still a hard time understanding the textbook. It was fascinating. There were long periods of concentrated activity using the software, like this student is doing, and tinkering in the constant back and forth. They didn't have to know the labels of the technical words. The one point the teacher got corrected for giving an incorrect explanation. The students had used the software and remembered how things worked. When this happened, the other students started to clap. This was an observing in the class. The students felt that they were being empowered as a group to feel like they learned something. See, this student is actually taking notes and writing down what he's observing. So literacy in this regard becomes a real tool for him to preserve the knowledge that he generated and communicate it to somebody else. We were working in something called the Educational Testing Services, or ETS, was going to evaluate with us evaluate this with a control group. The control group did not use Genscope. ETS does its testing using standardized literacy evaluation. So I started to work with the students. I'm coaching them to make a presentation. Look how he is using writing, which he had not done until the present. That's the way you really get into literacy, not by rote memorization, but by using literacy to support your conceptual understanding. It's not a world where you can understand unless you have an experience which you can relate to. My take of all of this, of having to work with the teams that would rotate, so the children had different teams. It was the first time a student was allowed to actually go to the board and do a presentation. And he had to ask for permission for this to happen, because this never really happened, that the children went to the board. It was complex and it was very controlled. He asked at the end, "Do you have any questions?" Everybody clapped and there was a bit of celebration. It was equally important that the teacher asked for the other students to see that the students were capable of doing something like this and that they were intelligent. Complex problem solving in genetics, just using the text was over their heads, impossible for them to make sense. Then they saw these Latino immigrant students learning from a computer simulation, not a book, and I realized that it was fundamentally transforming from orality to what I now call cybersy. Cybersy in certain features that distinguishes from digital literacy. Literacy is a very loaded word. The loaded tradition according to what the World Bank and the schools define as literacy. What I want to argue is that what is going on is not a form of literacy, but something that I call cybersy. When I was in those classrooms and I was reading the textbooks to them, I realized that these children were learning very complex systems thinking, something I learned as a biologist over many semesters. But the software is combining the DNA, the chromosomes, the genome process, and the process manifested itself in the organism. something a book cannot do very well. So everything I have learned in schools about evolution and genetics and biochemistry was being put together in a systemic way that put these concepts, students actually learning by doing. Any activity they do follow as the rules of the genetics was crucial. As a consequence, for their actions are actually visible at the level of the organism. So, for example, in this case, if you want to have a dragon with horns, a recessive genes, you will have to tinker with the genetic makeup of the parents, right? I mean, this is all conceptual. And this made completely transparent to the students. Students learn to tinker and see the result, creating their own theory of how this all works. Later, they move to the pedigree level and learn about inheritance. Students did not know the word DNA, RNA, gamete. They simply watched, observed, and that's the clip that I wanted to show you of the student making a presentation. At some point, the teacher gives the answer of the textbook, but the students interrupt and says, no, it's not true, because on the computer, this is not what happened. So what the teacher was presenting on the board was in fact wrong. The teacher admits the students is correct. The kids are smart. In fact, in these visually mediated simulations for conceptual understanding, enable students who don't come from a traditional illiterate background to understand is incredibly powerful idea for me. This is why I want to call it cybersea. But when NSF evaluated the students with paper and pencil exams, they did not do well, even though they could do it in the software simulation. Instead of seeing it as a door to literacy and to understanding complex things that they had just done, they were learning from actually doing things. I coached the students when they were at the seats to be able to recreate what they had talked about. At the end, he asks, and so he presents his findings in the board, and at the end, he actually asks, do you have any questions? In fact, this kid took the floor was transformational. It was made possible because the students was doing a visualization instead of forcing them to read from textbooks and to understand. That's it. Any questions? Oh. So let's look at different aspects of oral versus literate versus cybersea. Speech, text, and computers beyond digital literacy. So you have to go to the next slide. What I'm arguing is this. If we are going to call students who now play with laptops and iPads digital literacy, I think it's an oxymoron, because it's not literacy. It's an ideological word. Instead, it should be called cybersea, because they're learning on a cybernetic medium through computers. By the way, let me mention another simulation called RELAB that teaches relativity. Difficult for everybody. Because the software simulation, a Haitian immigrant student solved the twin paradox. Suppose that one of two identical twin sisters flies into space at nearly the speed of light. According to relativity, time runs more slowly on her spacecraft than it does on Earth. Therefore, when she returns to Earth, she will be younger than her Earth-bound twin sister. And then next slide. Oh, okay, thank you very much. Any questions, comments? All right, thanks.
Thank you, Dr. Catalina, for that enlightening talk. I think we agree that we learn we learn by doing, other than memorizing. There we foster critical thinking, problem solving, and creativity. I had just actually yesterday or last night when my daughter woke me up in the middle of the night just asking me about why climate change is happening. So I think that's when learning by doing really matters, other than just memorizing information. I would like to take this moment actually to remind you of your badges. If you notice at the back there are some barcodes, and it's really important that you scan these barcodes and take some of your time to evaluate and also to register and check the WhatsApp group as well, if you could join. Now we have reached the point in our schedule where everyone can take a well-deserved break and enjoy some lunch. Lunch is ready for you in the multipurpose hall. While you savor your meal, please remember that our parallel session will resume right after lunch. And be sure to check your programs for the specific times and locations for each session. Please note that we will reconvene here in the auditorium at 4 for the continuation of our program. Thank you. May I have your attention, please, that the parallel sessions will start at 1:30. Thank you very much.